Hello and welcome to another lesson for Math 1106, Math for Business Precalculus. My name is John Adamski. This is week 12, where we will be studying logarithmic functions. Now in week 10 we studied inverse functions, and last week in week 11 we studied exponential functions. And logarithmic functions are simply the inverse functions to the exponential functions. That is in fact their definition. So we will go over that definition of what a logarithm is. We will see, since it is an inverse function, that it obeys the cancellation equations that all inverse functions do. And we will define along the way what we mean by the natural logarithm. It turns out to be the inverse function to the natural exponential function, which we talked about last week. We will go over some log laws, some properties that logarithmic functions all have that may or may not be familiar to you from high school, but we'll go over that in detail. And one of those log laws is particularly useful in solving equations. So oftentimes when solving equations, we take logarithms of both sides of an equation. We will go over how that works, and we will talk about why it is you would do that. And lastly, we'll look at some graphs of logarithmic functions in general, and in particular, the graph of the natural exponential function. So let's get to it. So here's the definition of a logarithm. And really everything that follows in this lesson follows directly from what's inside this box right here. When I say log base a of y equals x, that tells you something about the numbers a, y, and x. And what it says about those numbers is exactly the same thing as what this says, which a to the x equals y. Now you're probably very comfortable with this because you have a lot of more experience raising numbers to powers and evaluating the result. So you're very comfortable with what the right-hand side is saying. The left-hand side is saying nothing more than that. It's just saying it in a different way. Okay, for example, you know that 2 cubed is 8. 2 times 2 times 2 is 8. You know this. And so the logarithmic way of saying this is to say that log base 2 of 8 is 3. That's it. What does that mean? Well, it means exactly what this means. What about this? 9 to the power 1/2 equals 3. We've talked about that. We know that raising something to the 1/2 power is the square root. So this is just saying that the square root of 9 is 3. And another way to say that using logarithms is to say that log base 9 of 3 is 1/2. Okay? That's it. And here's one more. 5 to the power -1 equals 1/5. Maybe you're picking up on the pattern. That's what I'm shooting for right now. That means that log base 5 of 1/5 is -1. All of these are true statements. All of these logarithmic statements are just restatements of these exponential statements. Okay? That is the definition of logarithms. Okay? Now maybe you're on to the fact that this is an inverse function. Okay? The idea here is that x is being input into the exponential function base a, and y is the output. And over here, y is the input into another function that I'm calling the logarithm base a, and x is the output. Okay? So we've switched the roles of inputs and outputs. Starting with x, if I take an exponential function, like a to the x, I get out y. And when I input y into the logarithmic function, base a, I get out x. They are inverse functions of one another. We make a similar diagram when we talk about f and f inverse. And so just to make that super clear, let's go ahead and introduce that notation. Let's call a to the x f of x. Okay? And let's call log base a of y f inverse of y. So this is just summarizing exactly what I was just saying, that these are inverse functions of one another. When x goes into the exponential base a, y comes out. When y goes into the logarithm base a, x comes out. These are inverse functions, and they obey the cancellation equations that inverse functions always obey. Okay? You might know that when it comes to inverse functions, f inverse of f of x is equal to x, right? Well, for these particular functions, let's just see what that does. So f inverse, I said f inverse was log base a. So this would be log base a of f of x. I said f of x is a to the x, so this is log base a of a to the x. And the claim is that this gets you right back to x, and we can see that because a to the x, we said a to the x is y, right? Or maybe I should look here. A to the x is y. So this is log base a of y. And what is log base a of y? Log base a of y is x. So you see it's following immediately from the definition. And so what I have here, if you can read between the lines, it says that log base a of a to the x is equal to x. That's a cancellation equation for log, and it's this one right here. Okay? The other one is to compose these functions in the reverse order, starting with f inverse inside of f. That would look like this. That would look like a to the power f inverse of y. So that would be a to the power log base a of y. So log base a of y goes upstairs here. What is that? Well, log base a of y. Log base a of y is x, so this is just a to the x. And what is a to the x? A to the x is y, so this is just y. Okay? So what is that saying? That's saying that a to the log base a of y is equal to y. There's nothing special about y here. If you just turn that y into an x, you get this cancellation equation. It's saying that when you compose these functions in either order, you get back right what you started with. Okay? And that turns out to be a very useful fact. Let's keep getting comfortable with logarithms with some more examples. Okay? So I've got example 1 on the board. It wants me to calculate log base 7 of 49. Okay? I'm going to do this in 2 ways. That's why this is both example 1 and 2. But log base 7 of 49, the first way I'd like you to think about it is if I'm going to use what's inside this box here, and the big claim is that this is kind of all you need to know. Log base 7 of 49, to make that a complete sentence, let's say that equals x. I do that because now it looks a lot like what's written on the left-hand side, where a is 7 and y is 49. Well, the other way to say it is right here on the right-hand side. The other way to say this is to say that 7 to the power x is equal to 49. Okay? Now, to go back and forth, what I like to do is I like to cover up the logarithm, okay? And leave the a, cover up just log, cover up log. And then it looks like it says a to the y equals x, which is not what you want. But if you switch the y and the x, and again, ignore this logarithm right here, then it says that a to the x equals y. And that's exactly what the other way to say this, okay, the exponential way of saying this. So that's how I got here. I'm covering up the logarithm and switching the position of x and 49, and then it says 7 to the x equals 49, and that's what I want. Does that help me know what x is? Ultimately, now I'm trying to figure out what x is. Hopefully, it does. Okay, hopefully we can see that what we're arriving at is that x equals 2. So the answer is 2. Okay, we can solve the next one, and the next one after that in similar ways. So this says that log base 2 of 32, I'm going to say equals x. So I'm introducing that part so that I can rephrase this statement, this complete sentence, in terms of exponentials. The trick is the same. I cover up the logarithm and I switch the positions of 32 and x, and I get the equation that says 2 to the x equals 32. Now this would be tricky if I put a number like 33 or 34 there. I don't know what power you'd have to raise 2 to get those numbers. That's tricky, and to be completely upfront, there are lots of logarithmic expressions that I could write down that I would need a calculator to tell you anything about. But those are not the questions that I'm going to be asking. This one is answerable without a calculator. 32 is a power of 2. 32 happens to be 2 to the 5th power. 2 times 2 times 2 times 2 times 2 is 32. So in this case, the answer is just 5. Okay, here's an interesting one. It says log base 4 of 1/16. Well, doing the same trick, I'll make this a complete sentence, equals x. And the other way to say this is to say that 4 to the x is equal to 1/16. Now that might not be super obvious what x is quite yet, but you know that 4 squared is equal to 16 for sure. 4 squared is 16. And so it stands to reason that 4 to the negative 2, remember that negative exponents make you take the reciprocal. So putting a negative sign in the exponent position flips this fraction and gives me 1 over 16. So knowing that 4 to the positive 2 is 16, I know that 4 to the negative 2 is 1 over 16. And so that helps me figure out that in this case, x is negative 2. OK? Cool. Now there are other ways to think about this, other ways to go about solving it. Of course, it boils down to the same thing, but I could answer these using the cancellation equations. OK? What I mean by that is when I come to this one and I look at log base 7 of 49, okay? What you're kind of seeing here is that without reference to x, I don't need to introduce the x. I can just make sense of log base 7 of 49. It's asking me to think of this number as a power of that number, okay? So if I just write this down as log base 7 of 7 squared, that's of course the same exact thing, right? But now you have this cancellation equation which says that when you're taking log base a of the exponential base a, that the two things essentially cancel out. So here you've got log base 7 of the exponential base 7. Those cancel out, and you get 2, which is the answer. I could do the same thing here. It's asking me, when you say log base 2 of 32, you're asking me to think of this number as a power of that number. If I write it down as such, it becomes really easy to answer this question. Log base 2 of 2 to the 5th power is 5. Okay? And lastly, this one's a little bit tricky, but we've discussed it already. I have to think of the number 1/16 as a power of 4. It's 4 to the negative 2. And once again, log base 4 of exponential base 4 cancels, and I get my final answer of negative 2. Okay, so there's a couple different ways you could think about this. And now let's test ourselves with some trickier examples, all right, or at least I think they're trickier. You can use any of the above methods that you want. I think this one begs to be solved using the cancellation equation. If I just switch from radical notation to exponential notation, I'm right there. Log base 3 of exponential base 3, they cancel. The answer is 1/2, okay? This one's a little trickier. We could do it either way. Maybe you want to, I don't know. You have to think of this number as a power of that number. Okay, so I'm not quite sure how you want to do that. But let's see. I can relate 25 to 5 by saying that 25 to the 1/2 power is 5. That's just saying that the square root of 25 is 5, which is true. And so 25 to the negative 1/2, same thing we were doing over here. When you take the exponent and you negate the exponent, you flip the fraction. That gives me the answer, okay? So this is sort of some side work here. I can see that 1/5 is a power of 25. So what I'm asked to do is take log base 25 of 25 to the negative 1/2. And of course, these logarithms and exponentials with the same base cancel each other out, and you get 1/2. I'm sorry, negative 1/2. This one is a little bit trickier, okay? You need to be able to think of 4 as a power of 8. And it's not a very nice power, but I can lead you to it. So let's see, 4 is of course 2 squared. Now that's not immediately helpful because 2 is not 8. I'm trying to think of 4 as a power of 8. The base here is 8. But 2 is a power of 8. It might not be your first thought, but the cubed root of 8 is 2. Okay, so this 2 right here is the cubed root of 8. And it's still being squared. And the rule for exponents says that you multiply these exponents together so that we see that 4 actually is a power of 8. It's 8 to the 2/3. And now I can complete this problem pretty easily by writing this 4 as an 8 to the 2/3. And the logarithm base 8 of the exponential base 8 cancels, and I get 2/3. So I've presented a couple different ways of thinking through these types of problems where you're asked to evaluate logarithms. But all of these methods are coming down to just what's inside of this box. So make sure you can write this down on your page and then refer to it to solve really any problem of using logarithms. Okay, so we understand in general what the logarithm base a is. It's the inverse of the exponential base a. And there's one exponential function, namely e to the x, that we use all the time in calculus. It's called the natural exponential function, e to the x. It's just an exponential function where the base e is this number right here, okay, 2.718281828. And this is given the letter E after Leonhard Euler, a German mathematician who was famous for using this, for all the work that he did regarding this particular function. But it's also jokingly called Andrew Jackson's number. Andrew Jackson was the 7th president of the United States, and he was elected to the presidency in the year 1828. So 7th president, 1828, ha ha ha. So this natural exponential function, just like any exponential function, has an inverse function. It's the logarithm base e. Okay? And since this is the one that we end up using so often, we give it this distinction and give it a special symbol, the natural logarithm. Okay? So ln means natural logarithm, and it is just the logarithm base e. Okay? It's the exponential function for the natural, it's the inverse function to the natural exponential function. Okay? While I'm at it, let me just point out a few facts about ln of x, because it can seem a little mysterious. Logarithms are already a little mysterious, and now I'm letting you know that the base is actually this nasty decimal number that has no pattern to its digits. But there are a few things you can say about ln. Okay? Remember that anything you can say using exponentials, you can say using logarithms. So I know that you're comfortable with this idea that e to the 0 equals 1, because any number to the 0th power is 1. And so how do you say this using logarithms? Well, you say that ln of 1 is equal to 0. That's true. Why is it true? Because it's only saying this in the form of logarithms. Okay? And what is this saying? E to the power 1 equals 1. Okay? Actually, sorry, that's false. E to the power 1 is equal to e, is what I meant to say. And how do you say that using logarithms? That ln of e is equal to 1. Okay? These are true facts. I just explained why they are true. Okay? And so these ones you're expected to know. Okay? And in particular this one, you're expected to know that the natural log of 1 is 0. All right? Now you have cancellation equations with the natural log just like you do with any other logarithm. When I write e to the ln of 3, maybe I should put down on the board what the cancellation equations look like. I thought I had it somewhere, but maybe I don't. E to the ln of x is equal to x, and ln of e to the x is equal to x. This is just the cancellation equations for any logarithm, but now I'm doing it for the natural logarithm. And so e to the ln, they cancel. They're inverse functions of one another. This is equal to 3. Okay? Ln of e, same thing. Okay? When you compose inverse functions, you get back what you started with. And here I have two ways of thinking about this one. I can say that e to the ln, those cancel. The answer is the square root of e. That's true. I could also do this another way. I could go back to square one, say this is e to the ln of e to the 1/2. And beginning on the inside, you have ln of e, those cancel, leave behind a 1/2 that is still in the exponent position. And e to the 1/2 is the same as the square root of e. So these are giving me the same answer both ways. Okay? Cool. Now, the logarithms, and all of the logarithms, obey what are called the log laws. I'm writing them down for the natural logarithm because this is the setting in which you'll see them most often. But just know that all of these facts that I'm about to go over are true for every logarithm, no matter what the base is. It's true when the base is e, but it's also true when the base is any other positive number. Okay, so I want to prove these. I want to show how these don't have to be just accepted at face value, but you can understand what they're saying. To do that most easily, I'm going to introduce some letters little a and little b. Little a will take the place of ln of big A, and little b will take the place of ln of big B. Okay. Now, while I'm at it, there's another way to say this, which is to say that e to the little a equals big A, and e to the little b equals big B. Hopefully we're starting to latch on to that. This is following from the definition of logarithms. Okay? And any statement you can say using logarithms, you can say using exponentials. All right? So with that out of the way, I'm ready to go and tackle these log laws. The first one starts out with ln of a times b. Okay? And just to appreciate what it's saying something about changing the operation and changing the order of operations. If you give me two numbers a and b, I can multiply them together first and then take their logarithm, or I can take their logarithms separately and then add those logarithms together, and I will get the same answer both ways. So one is using addition and one is using multiplication and one is using addition. But also one is taking the logarithm last and one is taking the logarithm first. So keep that in mind, okay? Here we have ln of ab. Well, to show you how this works, how this is going to reduce to just ln of a plus ln of b, let me write it this way. Let me write it as ln of e to the a times e to the b. Okay? Now I have rules for exponents that say, okay, same base, add the exponents. So this is ln of e to the a plus b. Okay? And when you have the natural exponential composed with the natural logarithm, they cancel. Okay? So what you have is just a plus b. And maybe you see where this is going. Little a is ln of a, little b is ln of b. And that's the proof of this first log law. Okay? Not so bad. The others are very similar. Let's just go through them very quickly. The second one is saying something about ln of a divided by b. So you can perform division of these numbers first and then take their logarithm, or you could take the logarithm of those numbers first and then take their difference. So the big thing to notice here is that we're going from division to subtraction. That's a sort of like degree of difficulty. That's a little bit of a simpler operation. Subtraction is simpler than division, and you can turn a division problem into a subtraction problem using logarithms. Okay? Matter of fact, I don't know if you've ever heard of a slide rule. A slide rule is just a mechanical little toy, basically, that you can use to multiply numbers with many decimal digits together. And it's a physical contraption. You physically manipulate this mechanical thing, and it spits out the answers to complicated multiplication and division questions. And it works because it uses logarithms and exploits the fact that adding things together is very easy. If you convert numbers into logarithms, then you can convert multiplication into addition. So these facts used to be used, even in grade school when people were actually using slide rules. If you're not familiar with slide rules, maybe Google it. But anyway, ln of a divided by b, the first thing I'm going to do is just write this as ln of e to the little a divided by e to the little b. Now I can use the exponential law that I know, which says that if you have the same base here, e and e, I subtract the exponents. This is ln of e to the a minus b. And now that we have the exponential, the natural exponential composed with the natural logarithm, they cancel, and we get a minus b, which is giving me exactly what I want, ln of a minus ln of b. Okay? And lastly, for the third law, which is the one that I'm going to use the most often, it's the one that is really crucial in solving a lot of equations. I'm going to start with ln of a to the power n. Okay? And I'm going to do what you might suspect I'm going to do. I'm going to replace big A with e to the little a. Okay? And now I have a rule for exponents that says nested exponents get multiplied together. So this is ln of e to the n times a. Okay? And the composition of the natural exponential and the natural logarithm cancel. I'm left with just n times a, and that is n times ln of big A, as claimed. Okay? So these are the log laws. You should know all of them, but in particular, number 3. Number 3 is the most useful. We use it all the time when solving equations, and now we'll take a look at how that works. All right, now logarithms turn out to be a very useful tool to have in our tool belt for solving equations. So I've got an equation on the board right here, and I want to discuss and walk you through exactly how I solve it. Notice, though, that this equation is a little unusual, not something that we've seen before, because the variable x that I'm trying to solve for is in the exponent position. Okay? So that's how I know that I'm going to have to take a logarithm at some point. And if you think about it, of course I am. To solve this, I have to eventually, fill in and justify the steps, but eventually get down to x equals a number. That's what it means to solve the equation. And you can kind of see that one thing that's going to have to happen at some point along the journey is that that exponent, x, is going to have to come downstairs. Okay? So notice that we've seen that happen when you take logarithms of an exponential expression. If you take the logarithm of an exponential expression, that exponent gets to come down as a coefficient. Okay? This is the mechanics of this log law, that exponent gets to come downstairs to the main floor. Okay? And if you're trying to solve for x, that has to happen. So log is the tool for the job. I'm going to be taking log of both sides, but not quite yet. Be careful. The first thing I want to do is isolate the exponential expression. Okay, that's important. I'm not taking log of both sides quite yet. First, I'm going to do as much as I can without using logarithms. Namely, I can subtract 15 from both sides. That'll give me 5 times 2 to the x over 6 equals 90 minus 15 is 75. Okay? And I can divide both sides by 5, perfectly fine. On the left-hand side, that'll leave me with 2 to the x over 6. And on the right-hand side, 75 divided by 5 is 15. Now I've isolated the exponential expression. The only thing on the left-hand side is 2 to the power, I don't know why I wrote a 2 here, 2 to the power x over 6. Okay? Now it's time to take logarithms. So I'll write it out as the next step. I take ln of the left-hand side equals ln of the right-hand side. Of course, that's 2 to the power x over 6, and this is 15. All right. And at the same time, you might even just write it down right away. I'm going to use the log law. This is the whole reason why I'm taking the logarithm of both sides, because I get to bring this exponent out front as a coefficient. So now I have x divided by 6 times the natural log of 2 is equal to ln of 15. Okay? And you can do this in 2 steps, or you can do it in 1 step. If I do it in 2, I'll multiply both sides by 6. So I'll multiply the left-hand side by 6, and I'll multiply the right-hand side by 6. Now I have x times ln of 2 equals 6 times ln of 15. And ln of 2 is just a number. Currently, x is being multiplied by that number. I'd like to undo that, and I'll do that by dividing by ln of 2, both sides. Okay, these ln of 2's obviously cancel, and I'm left with x equals 6 ln of 15 divided by ln of 2. Okay, now what is that? I don't really know. I can't pretend to know what the natural log of 15 nor the natural log of 2 is. You can use a calculator from this point to get the exact answer, but this is a precise answer. Okay, it's calculator ready in the sense that we have solved, in theory, I have the solution, but to actually numerically compute this, I do need a calculator. That is what it comes down to. Okay, so I consider this equation to be solved. Okay. Now let's just do the same thing, but in the context of a word problem. Let's see how that goes. Last week we looked at questions that were similar to this when we were talking about exponential models. So this says, suppose the number of bacteria in a culture is initially 160 and is found to be 200 5 hours later. Assuming exponential growth, when will the population reach 400? Now the part about assuming exponential growth is kind of important. Okay, assuming exponential growth, that means that I can model the population with an exponential function. That the population at time t is some constant times some base to the power t. Okay, and I'm actually going to have to find that function. Now this is a review from what we were doing last week, so maybe I can go a little quickly through this. I'm told that the population at time 0, which according to my model would be c times a to the 0, I'm told that that population is 160, okay? And since a to the 0th power is just 1, that tells me that c is 160. Cool. All right, now I know that c is 160. I'm also told that the population after 5 hours is 200. So the population after 5 hours is 200. But I also know that according to my model, the population after 5 hours should be c, which I now know is 160, times a to the 5th power. Okay? So I can work with this equation. I can divide both sides by 160, which is pretty nice. They have a lot of common factors. 200 divided by 160, it's the same as 20 divided by 16. They're both multiples of 4. 5 times 4 divided by 4 times 4. All right, a to the 5th is 5/4. And so I'll just finish this off by saying that a is 5/4 to the power 1/5. Okay, hopefully we're all on the same page there. I'm just taking the 5th root of both sides. And of course I do perform the multiplication of those exponents to just get a to the 1st is 5/4 to the 1/5. All right, so coming back to square one, I know that my population function, my population model, is 160 times 5/4 to the 1/5, all to the power t. Okay? Of course, the normal thing to do at this point is to multiply those exponents together, so that really the way I'd like to refer to it is the population at time t equals 160 times 5/4 to the power t over 5. Okay, that's my population model. Now, that's only step one. The question still remains, when will the population reach 400? So what I'm going to do is I'm going to set this equal to 400, and now I'm going to solve this equation for t. Okay? Which you notice, t is in the exponent position. So when solving equations for variables that are in the exponent, you know that a logarithm is going to come into play. But not too soon. I can first divide both sides by 160, which is essentially 40 divided by 16. They're both multiples of 4. We have 10 divided by 4. That's going to be, so we're going to have 5 over 4 to the t over 5. And all I'm saying is that when I divide both sides by 160 or divide 40 by 16, I get 10 over 4, which is 5 over 2. Okay? And now it's time to take logarithms. So from this step, I take log of both sides. That's ln of 5/4 to the power t over 5 equals ln of 5/2. At the same time that I do that, I see this coming. The exponent is going to come out front as a coefficient. So now the equation looks like this. T over 5 times ln of 5/4 equals ln of 5/2. Okay? And now I want to isolate the t, and I can do it actually in just one step. Currently, this t is being multiplied by ln of 5/4 and divided by 5. Well, to undo that, I will multiply it by 5 and divide it by ln of 5/4. That is to say, I'm going to multiply it by this fraction. I'm going to do the same thing to the other side of the equation because I have to maintain the balance of the equation. So 5 divided by ln of 5/4. Okay? And now you see that this 5 and this 5 cancel, of course. This natural log of 5/4 and this natural log of 5/4 cancel. We've got t alone on one side of the equation. And on the other side, well, there's nothing to really do here other than to just write it up as one big fraction. On top, we have 5 times ln of 5/2. So that's 5 times ln of 5/2. And on the bottom, I have ln of 5/4. All right, so that's my final answer. That's how I'm going to leave it. T is equal to this. Please, please, please don't start inventing your own log laws. There is a temptation, I'll admit, to see a 5 here and a 5 here and think that maybe they can kind of cancel out. Okay, but it doesn't work that way. All right, there's no log law that tells me how to simplify log of one thing divided by log of another. If these fractions were inside of one logarithm, yes, I have log laws for that. But don't start inventing your own log laws. There are 3 log laws. I showed you exactly what they are, and none of them apply to this scenario. So there's no way to clean this up, despite the fact that it might look like there is. Okay? So that's the solution, and this is how logarithms are used to solve equations. Lastly, let's take a look at the graphs of some logarithmic functions. Graphs of functions are convenient ways to just visualize a lot of different things about a function all at once. They can convey a lot of information in a convenient fashion. So let's look at how we could sketch the graphs of the logarithmic functions and how it summarizes some of the things we know about them. So coming back to the definition of logarithms, okay, they are the inverse functions of exponential functions. So to just remind us of some things about exponential functions and their graphs, suppose I know that p and q satisfy this equation, that a to the power p equals q. Okay? Well then, what I could say is that the point p comma q is on the graph y equals a to the x. Okay? If you let x equal p and you let y equal q, these values of p and q satisfy that equation. That was what we started with, right? A to the p is equal to q, right? So these values for x and y satisfy this equation, okay? On the other hand, if you know that a to the p equals q, then you know that log base a of q equals p, because those are the same statement. And if you know that log base a of q equals p, then graphically you could say that the point q comma p, okay, where that's x and that's y, is on the graph of y equals log base a of x. Okay, again, that's x, that's y. If you plug q in for x and p in for y, it says p equals log base a of q. That's what I'm saying. Okay, so what this is telling me is now I want to make the connection straight from here to here. Okay, since this is the same as that, which is the same as that, which is the same as that, these are saying the same exact thing. All right, and so cutting straight to the chase, if you have a point that's on the graph of this exponential function, then all you need to do is switch its x and y coordinates, and now you have a point that's on the graph of the logarithmic function with that same base. Okay? This is true not just for these pairs of functions, but for inverse functions in general. Okay, basically, I'm just reminding us of the fact that if xy is on the graph y equals f inverse of x, okay, then y comma x is on the graph of y equals f inverse of x. Actually, this is a little confusing. Let me change those from x, y to a comma b and b comma a. Okay? If a comma b is on the graph of y equals f of x, then b comma a is on the graph of y equals f inverse of x. Okay, this is saying that b is f of a, and this is saying that a is f inverse of b, which are equivalent statements. Okay, so this is a general fact about graphs of inverse functions that we talked about 2 weeks ago. Right now, I just need to talk about them in the context of exponentials and logarithms, which are inverse functions of each other. So coming over here, what I want to do is I want to sketch the graph of y equals log base 2 of x. And to begin with, I'm starting with the graph of the exponential function y equals 2 to the x. All right, I've got it plotted here. I've got a couple points that I know for sure are on this graph. And all I need to do is flip their coordinates, switch their x and y coordinates to get points that are on the graphs of the exponential, on the logarithmic graph. Okay, so one point at a time, 0, 1 is going to be flipped to be 1, 0. 1, 2 is going to flip to be 2, 1. 2, 4 is going to flip to be 4, 2. And 3, 8 is going to flip to be 8, 3. Okay? Now, I didn't put any points over here. Their y coordinates are all fractional, but what we can see is that the y coordinates are getting closer and closer to 0. Well, when I flip the x and y coordinates, that means that these x coordinates are going to get closer and closer to 0, and we're going to get a picture that looks just like this. Okay? And the general idea about graphs of functions and graphs of their inverse functions, in general, they are reflections of each other across the diagonal line with the equation y equals x. And you can see, it's not perfect, but these graphs are symmetric across that diagonal line. Okay? That's always going to be the case when the way you go from one graph to the other is by switching the x and y coordinates. Okay, switching the x and y coordinates has the effect of reflecting across this diagonal line y equals x. And so this is the graph y equals log base 2 of x. Okay? And one of the things that it conveys is its x-intercept. Okay? Its x-intercept is 1. So it tells us at a glance that log base 2 of 1 is 0. There are lots of ways to wrap our head around this fact, but just knowing that the x-intercept of the graph is 1 is very helpful. And that's true for all logarithmic functions because actually all exponential functions go through this point 0, 1. Hence, all logarithmic functions will go through this point 1, 0. Looking at the next one over, I want to sketch y equals ln of x. That's the logarithm base e. It's the inverse of the exponential function base e, or the natural exponential function. And like I was just saying, every exponential function goes through the point 0, 1. So does this one. 0, 1 is on the graph of e to the x. So 1, 0 is on the graph of its inverse, the natural logarithm. Here's 1, 0. The rest of the points are a little bit hard to put precisely down. I've got 1, e, okay, when x is 1, y is e. Remember, e is about 2.7, so the y coordinate here is about 2.7. And when I flip its x and y, I get e, 1. So I know that I'm plotting a point whose y coordinate is 1, and I'm trying to get as close as I can to getting its x coordinate equal to e. That's about 2.7. I have it roughly in the right spot. It's going to be hard to plot any other points precisely. I can kind of fudge it by saying, well, okay, I already kind of fudged it over here. I was trying to say that when x equals 3, y is, of course, e to the third power. And if you round e to 3, e is actually a little bit less than 3. Sorry, I meant to say, sorry, that's a mistake. I meant to say 2, e squared, okay? E is a little bit less than 3, so e squared should be a little bit less than 3 squared. It should be a little bit less than 9. So I put this point where its y coordinate is a little bit less than 9. It's close to 8. And when I reflect it, I'll get the point e squared, 2. Now that's a little bit hard. I know the y coordinate is 2, but where exactly is e squared on the x-axis? Well, I don't know exactly, but like I said, e is a little bit less than 3, so e squared is a little bit less than 9. Okay, so I put it roughly where it belongs. And now I'm just going to connect the dots, again, knowing that on the natural exponential graph, the y coordinates are approaching 0. On the logarithmic graph, where x and y are switched, the x coordinates are going to be approaching 0. So I'm getting this shape for the graph. Okay? And notice that as you follow this tail, the x coordinates are getting closer and closer to 0, like I just said. This is the graph y equals ln of x. And it conveys this one important fact that I'm only emphasizing because it's used quite a bit, and most calculus students forget it all the time. But ln of 1 is 0, and that's showing itself in the graph by saying the x-intercept of this graph is 1. Okay? When x is 1, y is 0. So ln of 1 is 0. It's also pointing out that ln of e is 1, which is the other fact that you should know. But that's a little bit harder to see because that point is not really so precise, whereas this has integer coordinates, so it's very nice. So anyway, this is what the graphs of of logarithmic functions look like. You can see that, I mean, they don't look very different from each other. In fact, the numbers 2 and e are pretty similar, but the log base any number, all logarithmic graphs are reflections of their exponential graphs, and they all look very similar. Okay? So this is how you sketch the graphs of a logarithm by plotting points.